Can you give me an introduction?
Yes, I am. Today we are delighted to have Jeff Ibbotson. We'll be talking about the many faces of the Pythagorean Theorem. Just a reminder that the whole point is to be interactive and that everyone understands everything.
What? Oh, that does it. I'm out of here.
So at any point, please ask questions. Please ask for more examples. Please ask for a more correct diagram. And at any point, so that we can all stay on top of him, metaphorically speaking.
I hate when the students do this. What, throw it on the floor? Well. Okay, so, yeah, so you've already had a careful, rigorous talk from Chelsea. So my talk today is going to be more of like off-the-cuff reminiscences of Pythagoras. So times when we used to go bowling, things like the Pythagorean theorem is the most famous theorem in mathematics, I think.
Go ahead.
I don't know, it's a very weird statement.
Really?
That's fine, yeah.
What's more famous than that? The Gauss
I really
theorem?
don't know. I know so little of mathematics and so little humanity. I don't know what the most famous theorem is.
Well, it's certainly one of the most proven, right? There's something like between 200 and 300 collected proofs, and it's been one of those things that many, oh, hello there.
Yeah, that guy.
Many famous people have produced proofs in their day. You know, we are probably familiar with at least one of Euclid's proofs. This is the only result that Euclid proves twice in the Elements. It's the only one. It's at the end of book 1, because he thinks it's so important. It's proposition 47. And then later on, he produces a proof that is what most people are familiar with. Yeah, so just freehand drawing the squares, so who knows. But the idea is that this area plus this area is supposed to equal this area, often leading to dissection proofs. Most of the time, most students across the world will see a proof that looks something like this. Here's C, so C is equal to C1 plus C2. And here's A and here's B. And I have 3 similar triangles, right? So if this angle is 1 and this angle is 2, that means, since this is 90 degrees, this angle must be 1 and this angle must be 2. And notice what I need to be able to do this proof. I need to know that the sum of the angles in a triangle is 180 degrees. So that's a little controversial. I guess it's not controversial to us, but in its day, that has to do with the statement of the parallel postulate, and the parallel postulate is not true in all geometries. Right? Draw geodesics on a sphere, and we can see, oh, the angles don't add up. Here, in order to use this similarity argument, right, it looks something like this. How do I show that A plus, I want to show.
Wait, quick question.
Yeah.
Are you suggesting then that there are proofs that do not require the parallel postulate so that the Pythagorean theorem works in all geometries?
That is in fact exactly what I. This is what I want to prove if I want to prove, right? And I can see, for instance, that because these are similar, I have ratios to work with. So, for instance, if I'm looking at this H, maybe if I'm looking at angle 2, then I know C1 over A is the same thing as this way. So angle 2 would put H over B, right? And C2 is to be as
Just A.
just A.
H is A.
H is A.
Long
yes.
side over hypotenuse.
Right. And moreover, both of these are similar to the biggest triangle. So when I'm considering the small adjacent side to angle 1, for the big one, that's going to be A is to C1 plus C2. This is going to be the same as, let's say this is again, same idea. So that's
H. No,
H is to,
sorry, B over C1 plus C2.
so when I'm looking at this now, if I cross multiply, I see the B squared is C2 times C1 plus C2. And if I'm looking at this, I get A squared is equal to C1, I hope, C1 plus C2. So if I add them together, I simply get C1 plus C2 squared.
Ooh.
Just distributing, right? This plus this, so C1 times C1 plus C2, C2 times C1 plus C2 is, of course, the same thing as factor this C1 plus C2 out, just times C1 plus C2.
So we never needed H in the end.
We never need it.
Okay.
We shouldn't have anyway. This depends on knowing that the sum of the angles in this particular triangle, or any triangle, is 180 degrees. That's not the first proof that Euclid gives.
Oh, you want me to get one?
I just throw away a broken ruler. You could. Yeah, I guess.
There's a bunch of those next door.
Yeah, he's going next door to the right. What?
Yeah, I don't have a yardstick. Probably just for yardstick.
I had like 8 in my closet and I put them all in the outer supply room. So there's ones there.
So Euclid's original proof kind of works. So this is my A, in other words, this is my B, and this is my C. But what he's going to show is he's going to show if I drop a straight line down here that is perpendicular to this and to this, that then this area is equal to this area, and this area is equal to this area. And that's kind of nice. Sometimes you see this in science museums, right?
What? How does this work?
Well, I haven't done it yet.
Oh, okay.
Just telling you where I'm going. The details are forthcoming. Sometimes you see this done with like colored beads and things like that, right? The whole thing rotates in science museums, so you can see these beads fall down, and they exactly fill this. And the same thing here, they exactly fill that side. You say, oh, look. So this area plus this area equals this area. So if you do it. Well, a couple steps. So good. Until that point. So I claim that the area here is twice the area in this rectangle, the triangle that I just drew.
The area of the whole square or the area that's left?
This square
Yeah,
is equal to the blue area here
times 2?
times 2. You might see that if you recall that the area of a triangle is 1/2 base times height.
Ah.
So here's a height. It's the same as this height, and here's the base. So,
He's done some
Since
triangle
it's a
sliding.
square, so they, that's great.
yeah, 1/2 base times height in this case is, and now I need to label these points. 1/2 JB times this height, which is the same as AJ.
Sweet.
It is pretty sweet.
I'm gonna use a different color for the other one.
Maybe, well, it's all right, I got this and it's pretty good work. Like it. Next, I claim that the same thing is true for this triangle.
No.
Being, so this triangle, yeah, it's a triangle. Is half the area of this rectangle. Same idea, I can extend this and I can see how this is the altitude. It's not the same things. And so, am I done? Oh, I'm not done because I've got 2 triangles in the picture. But notice that these 2 triangles are congruent. Astounding. You say, no, false, wrong. Well, this length is the same as this length because it's a square. And, oh, this length is the same as this length because it's a square. And what's the angle? Well, so I'm going to do something very not Greek, not Euclid. But I can see it's 90 degrees plus this angle. And likewise, in this guy, this is 90 degrees plus the same angle. So SAS says those 2 triangles are. I think I'm done. Can you write the steps up?
Yep.
So the steps are as follows. The area of JB, so first of all, JBC is congruent to triangle AB.
Can you draw in the height that goes, I'm sorry to ask this mundane question, but can you draw in the height that goes to the base of A for me for that triangle A, B, E? I'm having a hard time visualizing that.
Extend it like this. And the height goes from, it's basically this, right? This is the height. You can see it goes from this point to this side, right?
I can't see it, I don't know why. Where is it? We're using A as side A as the base or
Different
side
color, different color will be, use a different color.
No, DE will be the best.
DE is the base.
This, which is the same as this.
Oh, okay.
I had to draw a different picture to understand, it would be helpful for you to put that separately.
Well, I mean, I didn't know where, I couldn't picture the height, but I mean, if I
I'm
try to
cutting
picture
through-
another way, there's no
I'm
guarantee that that
cutting
one.
through a lot of details here, right?
Yeah.
So if I was doing this as a talk for students, I would definitely go slower, and I would break this down into many different pieces. And also try to get a better picture, because it sure as hell doesn't look like it's actually the same thing. They are. And it's in the quest of finding an easier proof that this,
Fine, it's great, I just need, I'm sorry.
it's okay.
So does this not rely on parallel postulate either?
Where have I used it?
Oh. Base
thing that
times
you
the
didn't
bases
draw.
and the heights.
I thought like.
As the area of a triangle?
Well,
The thing that you didn't draw is the thing whose area is actually equal to the area of the square, which is a parallelogram.
Like, are you using the parallel postulate when you construct a square? Or no?
Well, construction is one thing, right? So, but I mean, certainly the axioms allow us to say there is a square. I can just invoke the axioms.
even on a sphere?
Right, I guess my point is that don't you need the parallel postulate to be able to say squares exist and they have, like, you can have 4 things that have congruent sides.
Yeah.
But can you then prove that they all have 4 right angles or?
So, right, what's the, yeah.
Because I remember vaguely recollecting sometime way back in the before times of taking a geometry course and me being astounded by something like this, and maybe I'm misremembering, but.
No, I mean, this is the proof as Euclid generates it. Of course, Euclid's not 100% rigorous, right? I mean, we have to wait until Hilbert, right? Basically for a fully rigorous version of Euclidean geometry. And there could well be stuff that's swept under the carpet.
This only works in the plane. Because if if the squares are 90 degrees and they have positive area, then you can't do it on a sphere.
Okay.
So that's okay though. We like it in the plane.
Yeah.
We live
Still a nice
in
curve.
Euclidean
Because in the
space.
plane,
What?
because we're on the plane.
Yeah.
That's why it's.
So is Pythagorean theorem true
Okay.
in other geometries?
I don't know.
For me, the key to this argument is that if you shear something parallel to one of its sides, then its area remains the same. Cavalier's theorem. And that, I mean, I use the word parallel, and the word parallel is absolutely necessary for that statement of theorem. In the curved geometry, that would absolutely not be true.
So in a sphere, you can, I mean, it's very difficult having parallel lines, right? In fact, if I draw one of these great circles, there's no other classically that's parallel to that.
So is Pythagorean theorem still true in other geometries, or is it only true in? Sorry.
No, it's
Am I ruining
quite all
you?
right. I get that. The physicist's answer is this, that infinitesimally speaking, it's always true. And that I can use that when I talk about surfaces. Things like that.
Yeah, that's
So
why I said these
locally
have to
it's
have a
always
positive area. Because infinitesimally, the Pythagorean theorem holds, but if it has positive area, it won't.
Okay, so you're saying locally it's always true.
I am. Rather Euclid is. So the areas are the same. This is what we proved, right? These two are congruent. And moreover, the areas are equal. In particular, twice the areas are equal. So therefore, it follows that the area of the square DJ and this rectangle, which is fully named, have the same area. That's the steps. And I can do the same thing on the other side. Obviously, it's completely symmetric. And when you get the full range of proof that's actually going on here, this conflux of lines is sometimes called either the windmill proof or the bride's chair. Traditionally, this is the first proof. So you may not like it. I mean, it doesn't seem extraordinarily visual until you kind of pore over it for a while and see why it's true, but it seems to only use some elementary facts about area of the triangle and so forth.
So you were saying this is a proof that Euclid did it?
Yes, it's in the elements, right? But I guess I can say a word about that. We actually don't know what's in the elements. What we have is the Eudemian summary of Euclid's elements, and then we have like lots of other versions that have been discovered later in time. And they're all consistent. So we believe there's this OR object called Euclid's elements, but we don't have like the original copy. So we're making some assumptions.
Do we believe Euclid wrote it or did his school write it?
Well, it's hard to know, right? As far as we know, there was only one Euclid, but Euclid lived in Alexandria in northern Egypt. So this is in sort of late Hellenic times. Could it have been the product of many people's work? Sure. In particular, in order to talk about similar triangles and comparing lengths and stuff here, he has to actually invoke the work of Eudoxus, right? Because these ratios, they could be irrational quantities. So it's Eudoxus who figures out how to actually process statements like this.
Without getting thrown in the river.
Without getting thrown in the river, yes. So here's another kind of nice, more visual proof of the Pythagorean theorem. You'll notice how carefully I'm measuring this. So. This one is due to ostensibly Leonardo da Vinci.
Why were you measuring so carefully at first?
So as to give the illusion of precision without actually achieving any of the nice results.
Are those squares?
These are squares.
All three of them?
These are, yes, everything's a square. A, B, this is B. This is triangle, this is C. This is the same. This is the same triangle here, and this is the same triangle over here, right? Okay. And what I need to do is to draw.
What's the matter?
Yeah. I thought it was pretty straight.
Pretty good. Yeah.
But it's going to put
So
Forward is good. Things to learn.
if you look at this figure carefully, you can kind of see a quadrilateral repeated 4 times.
What?
Yeah. So the quadrilateral, so I'll shade it for you. So here's the quadrilateral. Notice this is the same quadrilateral. Oh. Thank you, Chelsea. About 4 colors. This is an even worse experience.
Bless you.
Oh.
There's a fourth one there.
Yeah.
Open without a cover.
You went over some of the red.
No,
That's why I say, you open, don't put any
it's
cover.
the idea that's important, right? Oh, I did. Yeah, that's intentional.
Yeah.
It's cross-hatched, right? So I'm saying orange plus green is equal to red plus blue.
What is that?
So that's okay.
And that's the Pythagorean theorem.
Let's read it out.
Let's read it out. Orange plus green is this plus this, so it's the area here, plus the area here, plus twice the triangle area. Red plus blue is this area here, plus twice the triangle. I'm done.
You have to justify your first line.
Of course!
You're done modulo 11.
We rarely talk about congruence for a quadrilateral like that.
Right.
So if I really want to say, oh, these are all congruent, I have to use apparently side angle, side angle, side. Maybe another angle inside, but I don't think I need it. I think that'll do it. So, so yeah, this is a bit dicey as far as what our assumptions are, but angle, side, angle, side, angle, side, congruence,
I think you don't need the first angle,
probably not. I just
because
figured,
it's very hard to get that first angle.
yeah, fair enough.
Wait, that's,
I didn't, because now Gwen's gonna get upset at me and then I'm gonna have to like say something.
Why am I doing this?
I don't know.
So the
wait, so
two
trapeze
that you're
is-
looking at there,
Yeah.
those seem to be just related by a rotation
This and this?
or a reflection.
A reflection, yeah, for sure, right, just the bigger angle is from here. Yeah, so that's not, you see, that's not hard to see rather. Of course, reflections are really in Euclid. Right, so if I'm playing this, you know, but it's more than 1,000 years later, right? So I guess we're talking about different assumptions and maybe some sense of aesthetics involved or something like that, but yeah.
So what? So I've just never heard of it called as a trapezoidal. Is that just another name for quadrilateral?
It's not did I say trapezoidal?
Okay. I was gonna say, because that doesn't look like a trapezoid to me.
Beg your pardon. And here's some of that famous imprecision coming in. I just wrote that there just to see if anyone was paying attention. Yeah, there's some parallel signs. It's not a
But so how do we know though that those are actually lines?
Which one? The dashed ones?
Yeah, like, I mean, it's not obvious to me that
They have to go to that point.
that they go through the points that you want them to go through.
Yeah.
Which points do they have to go?
Those are the 2 points used.
If it was drawn, scale probably.
Well, I mean, there's 3 points on the leftmost dotted line that you're going through.
This one?
Yeah.
We're coming
Oh,
two
oh,
squares,
oh,
so
okay.
it's like
Oh,
slope
that one,
negative
yeah,
1.
yeah.
Or does it not need to go through that point in the square?
No, it does. In fact, if you draw this carefully, you find out that this is a right angle. Which is kind of intriguing. It says I could put a different
Oh, no,
coordinate
that's-
system on this whole thing.
But so we have to convince ourselves though, right, that is it going through all those good points. Is that-
Yeah.
Well,
You're
Those-
putting
I think
together
those three?
only for the left
two
line,
squares.
right?
Yeah, for the right line, there's only 2 points to go
Yeah.
through.
You don't need this. The square, so it's like at a 45-degree angle. And so it's
So
that.
is that.
The question, yeah, the question
And
is
these
if you
two are
put,
parallel.
if you draw a cross.
Ah, okay,
you put
yeah.
the squares, yeah.
The extra triangles are throwing me off. Yeah, no, I see what you're saying now.
Other questions? I think it's nice. I mean, yes, it's not, you know, how rigorous are these proofs? You have
Well,
to.
how does this prove Pythagorean theorem though? So let's look on that.
Oh, yeah, the Pythagorean theorem says the area of this square plus the area of this square is equal to this square on the hypotenuse.
So can you write out orange plus green is like,
So orange
squared plus
plus
b
green is equal to this square, so the b squared part, plus 2 of these same triangles, plus this, a squared, plus 2 of the same triangles.
which is just AB, but that's okay.
Right. And that's equal to red plus blue, which is c squared, plus, again, 2 of the same triangles. Yeah. Other
So that's the third method, right?
third method, which is due to a
President.
President, James Garfield.
And an alum of Williams College,
Apparently, I didn't know that. So that's
like 3 of our people in the math department.
So this one is James Garfield, you said?
this is James Garfield. Yeah. That's not really. Let me do this via the actual figure. I'm going to take the triangle. I'm going to take this triangle, which let's say looks like this.
Can I ask how does this relate to Leonardo da Vinci? I missed that part.
Which part?
Why is it related to
I didn't know that.
Leonardo da Vinci? The name you write here.
Oh, why Da Vinci?
Uh-huh,
Oh,
yeah.
because as far as we know, he came up with it.
Oh, okay.
Da Vinci had mathematical friends, and in particular, one of his friends was Luca Pacioli. And he was somebody who really popularized mathematics during the day. So this is like
Oh,
14th century Renaissance Italy.
You teach the history of math class, right?
Oh, Kevin,
Part of this?
I don't. Yeah, history.
Are we allowed to sit in on another? Yeah, we'll have the time for it.
Anytime. Just Just come, just, you don't have to ask anything. Just, or I have materials too. So I can put them on the table if anybody wants to put them upstairs. If I take this triangle, so this is Garfield's proof, right? And now, so, yeah, Kevin's right, I should really try and use actual lengths.
Too late.
Now it's just the framework. That's 6 to 15, so I'm gonna go like here. And then I'm gonna go at 90 degrees. Something like that, so that's 21. So that is a trapezoid. This is James Garfield, circa 1830s, 1840s. James Garfield was a math teacher in Ohio. Who later ran for Congress as part of kind of compromise was worked out between states in the north and the south, and eventually became president. Somewhat surprising, but if you go to Cleveland, Ohio, that's where his spoon collection is. Spoon? Spoon collection. He apparently collected spoons.
You know, that was a thing.
Decorative commemorative spoons. It's still a thing. You can buy them in the airports.
This is, so if I recall, the area of a trapezoid, I can just average these two sides, right? And then multiply by this, which is certainly a height. So the area here is 1/2 the average of A. So that's the average. Multiplied by A plus B, which of course gives me 1/2 A squared plus 2A plus B squared. And oh, I also have to add in this, right? Sorry. Incorrect. If I look
That's
at
the
this,
area of the whole thing.
this is the area of the whole thing. This is equal to 1/2 C squared plus 2 of these guys. Again, right? If I multiply through, or I don't even need to do that. If I cancel the 1/2s, I have A squared plus B squared plus, in this case, I have AB. And this side, I have C squared plus.
I think if you cancel 1/2, you have to keep the 2 on the
The
AB,
twos.
but they go away anyway.
Yeah.
But you might as well throw it in there.
At no point during this entire time did my hands leave the ends of my arms. And I'm not using notes. So that's Garfield's proof. It's kind of nice. It's published like in a math teacher around the day back in the 1830s. James Garfield, unfortunately assassinated, never really became president very long. He was assassinated by
Where was he going when he was assassinated?
he was apparently going to Williams College for his reunion, which has since been advertised by the college as a reason that people should not go to reunions.
He was assassinated, of course, by someone who had him as a math teacher.
No, actually not. He was assassinated by somebody who believed he deserved political office. And so he wrote to him saying, you're going to want to give me a job as chief dog commissioner of the Northwest or something. Garfield didn't, and so that's why. Okay, well, so this is the situation plus 100 other proofs that I'm not going to show you. Up until 2002. And then an unknown mathematician said, you know, I really want to extract like the what's behind the Pythagorean theorem. Like, why is it? What is it that makes it work? And so this unknown mathematician said, you know, we teach in Math 2 that lines really come equipped with normals. AX plus BY equals C, right? It's in Math 2, AB is a normal. So what if I consider normal vectors on these three sides that each have the length of this side? Well, that's kind of an interesting idea because I wind up getting three vectors. I'll call them U and V and W, and I claim that they add up to 0. Now, I have to state this again, right? The magnitude of U is equal to the length of this side, AB. Right? And the magnitude of V is equal to length of AC, and the magnitude of W is equal to AC. You believe it? No. How about this? Do these three vectors add up to 0? Yes.
Yeah, I believe that.
Oh, well, then the others are just rotated by 90 degrees. All in the same direction.
I understand.
Nicely.
Why are we getting the dining hall?
Why, what?
It's okay.
So each one of these guys, right, is just equal to the side vector, but rotated. In this case, I guess in a clockwise direction, if I'm going like this. And this is rotated, again, clockwise 90 degrees, and this guy is rotated clockwise 90 degrees. And they add up to 0. So this is true. And secondly, notice that then this says W is equal to minus U plus minus V. And this is a perpendicular decomposition of this vector. There's my basis. The negative of that vector, obviously, right? This plus this, they're orthogonal. They have no components in common. Therefore, the magnitude squared of this thing equals the magnitude of this thing plus the other.
Because it's orthogonal.
Because it's orthogonal. Right, so it's kind of reduced to, I guess, what would be a simple linear algebra proof. Right, you to actually prove that, you'd have to say something like the magnitude squared is W dot W. And that's equal to, stuck with this minus sign, minus U plus minus V dotted with itself. Right? And then I apply the distributive law, and then every time I have a V dot U, that's 0. Yeah. So at some point you kind of look at this and you go, well, wow, this feels like a scam, as my calculus students or my geometry students would say. That's a scam. Because, you know, really, how did we define the magnitude of a vector anyway?
Use the Pythagorean theorem.
Right. So it's a little circular, but my goal was not to reprove the Pythagorean theorem, but to rather extend it. Because if I can do this for a triangle, then I don't see why I can't do it for a tetrahedron. So what if I do that over here? Is this too far away? Or I can erase. I'll erase the So. Shouldn't have done that. Start over. So. Here's a right tetrahedron.
Wait, in that proof, Jeff?
Yeah.
Why do they have to be a normal to each side? Why couldn't you just use the side vectors where they are?
I could have, but yeah, I could.
It doesn't add anything, right?
No, but here it does.
Oh, okay.
To the 3D case.
Okay.
So I'm going to do the same thing, right? If these three triangular faces all meet at right angles, I'll call this a right tetrahedron.
So it's like the corner cut off of a box.
Correct. And I can do the same thing, but now I'm putting normal vectors. So let's say n1, n2, n3 on each of these sides, where the magnitude of these guys is the area. Of the face to which it's associated. And so this fourth face cutting through here is also has one, right? Perhaps it looks like that. Call it W. And again, the sum of those is 0. So that's not as obvious. But in a sense, you can see it visually, right? Because if I look at the negative, it's like these three vectors are all perpendicular. And they form a reference frame, right? So 3 perpendicular vectors form a reference frame. It should be enough to decompose this. So I want to say W is equal to minus n plus minus n2 plus minus n3. And because they're perpendicular, when I take magnitudes of each side, it tells me the area squared. That's right.
You have 3 minutes left? 3 minutes left?
3 minutes, okay. The area squared of this is equal to the sum of the squares of the other areas. Now that strikes me as kind of an interesting thing. So.
But you haven't justified why W equals N1
Yeah.
plus N2 plus N3s
Okay.
when they spell them by the areas.
Okay.
Well, it's not obvious to
It's
some of
not.
us.
So let me describe the tetrahedron with 3 vectors U, V, and W. E and R that come down from that top point. And notice that, well, if I take like U cross R and I take the cross product, that's the vector I'm looking for.
Can you remind us what the cross product is? Because I don't.
Sure. If I have 2 vectors, V and W, let's say, then the cross product is always perpendicular to these. So it comes out at 90 degrees and it carries the area of the parallelogram. It's really 1/2 the cross product. I'll assume that I can cancel the 1/2s between friends. So if I write this out, so this I did write down, just to double check. Then N1 here is, did I say it? What is it? It's U, so if I go this way, it goes this way, so it must be R cross U, I think. And N2 is going to wind up being V cross R. And N3, which is down here, oh, now I need a difference, right? So it's going to be the difference of,
R minus U.
yeah. crossed with the other
R
difference.
minus V.
V minus R.
Okay, sure. Minus,
That's minus.
instead of times there.
In between,
You're gonna need minus.
not across.
Oh, that one's good. That one was,
Okay.
no.
The cross
This is
and the minus.
minus V.
R minus V, I think.
And that's
Yes,
across.
this is indeed cross. Yeah. Good. And it distributes and everything works out nicely. So I guess I'll leave that as an exercise for the reader. but
What does it work out to be? One distributes nicely?
Oh, yes, right, indeed.
I believe you, but
It should turn out to be the same as the cross product for the big face, which is the negative of U cross V. Is that right? U is here. This negative, so yeah, negative. So once I've done that, I've shown that I can decompose the vector like this, and then it's true for the areas. There doesn't seem to be anything special about 3 dimensions here. At what point did I use 3 dimensions? Well, one
when you use the
problem
cross product.
is that the cross product has dimensionality associated with it. But if you can't define a cross product in all dimensions, at least it has the typical properties. So in fact, I don't know what it's 5 after this and then maybe 7. And then, it's related to the Vedderburn characterization theorem for algebra. So
But I don't think we ever use the cross product really, and I don't think it's a scam because the vectors E and W are the row vectors,
right.
that measure how much area each line sweeps out when you do that. That doesn't require the Pythagorean theorem to say.
Exactly.
But
Exactly.
That's where we're going.
No, quite right. Or I can use, well, you just basically said it, the Graham determinant, right? Which is going to, so that just uses dot products embedded in a matrix, and that gives us something. So this should be true for all n dimensions. That there is a version of the Pythagorean theorem that works for the relevant sub, whatever it is, hypervolumes of the faces.
I propose, Jeff, if we can have like teams, right? We can break down, if each one takes maybe one of the things, and we try even to use a computer visualization, right? And try to have it as a school of Pythagorean theorem or something like that, or class. And that would be nice, even if you have, like our perhaps coming to visit, so we can show them this stuff. I mean, it's
Sure.
very, I mean, if you can break it down. So the methods are very nice, but I think, even for the teachers we are, it's a bit, tough for because if we can take one, instead of, doing this thing, right, we take just one method. We all come and we come together and try. I know Aaron likes to do things in, with a lot of computer simulations and things like that. Also doing this, that'd be nice, I can bring my algebraic, stuff on, but then we can try to sit and put them as, nice.
Well, I don't want to deceive
You don't
you.
want to
So
do it.
even though I thought about this on my own, it's known. It's pretty well known, so we're not breaking ground. that is gonna be
I'm not talking about
wrong.
that, but I'm
Is
saying
the
at least.
goal to create a library of different groups of the Pythagorean theorem, which we could then use as a course material? Or
I just throw the idea, because I think
I just want to
it
understand.
would be nice, like even, I'm sure
Yeah.
some of our back students can do this things. I have my classes, I know I have 2 or 3. If you ask them to sit.
Oh, no, that is interesting. So, I mean, you could, in places in our material, you could have a little hyperlink or a comment saying, if you enjoyed this, you might be interested in using these videos to prove Pythagorean theorem. There's a connection into our materials for lots of this stuff. So I think that's kind of what you're saying, that it's this would be accessible to kids, you'd like to see more.
Kind of, yes. I was not related to the material, but now you say, I think it would be even much resourceful to point out those in the curriculum and aids and this week.
Okay, I have to leave you with one other result, so I'm just gonna mention this, and again, this is the.
You're not gonna finish with Chiang-Kai's proof? Just kidding. You,
Chiang-Kai's proof is this.
When you
thing
said it
that
was-
also has somebody's name attached to it.
well, when you said it was an obscure mathematician in 2001 or whatever,
Yeah,
you weren't the first person I thought of, but now you will be.
I'll just generalize the Pythagorean theorem to show that it doesn't even need to be seen as about right triangles. Now, so that idea right there suddenly strikes my heart with fear, because as far as I know, right, these ideas lead you to believe, oh yeah, that like vector decomposition, there's got to be some orthogonality, right? And plus, we're looking at squares, things like that. Papa says, no, I can put any two parallelograms on any triangle. And as long as I do this, so extend the sides, so they meet at a point H, and then use this vector, so this is really the vector BH or HB, it has the same length, and is going in the same direction to draw a parallelogram on the third side, then this area plus this area equals this area. And the proof is beautifully simple if you remember it. If I just take this and put it over here, and I also put it over here, I can see that, well, the area in this parallelogram is the same as the area in this parallelogram. And if I drop a line straight down like this, going in the same direction, BH, that's the same as the area here. And the same on the other side. So I find this rather surprising. I mean, this makes it look like it's something beyond even vector decomposition.
Wait a second, so you're saying,
I'm saying that the area in this parallelogram on this side, which I just drew,
like any
parallelogram, and this parallelogram, which again, I just drew, free choice. And then I construct this point by extending these sides and connect it to the top here, and use that to determine the side of my parallelogram down here on the base. They add up. The areas add up.
So the base is a parallelogram also?
The base is a parallelogram.
Is it a rectangular?
Because it looks like
Because the AI know I've drawn it like it's a rectangle, because the way I drew this picture, it actually looks like that's perpendicular, but this doesn't need to be.
Okay.
It can be anything.
It's because you made the other two so
Can I draw
close
a
to each
picture
other.
and ask how you would do it for like a weirdly shaped
You see
one?
this triangle? It's the same as decomposing a little triangle at the top, right? It's basically similar to that same thing. So you create a version of this area addition inside itself.
It's the same proof, right?
Yeah.
The proof is that the three row vectors, that if the area is swapped out by the three sides, it adds to 0.
Can I just ask how you construct a pair of parallelograms for a weird example so I can better understand it?
Sure. We should maybe thank Jeff and let people go to do different
Okay.
things, and then we can ask more questions. Thank you, Jeff, for this
Yeah.
wonderful talk. Nice job.
It's like why something happens to 0. Now I'm like, oh, it's amazing. So normally